So now that we've determined end behavior, now we're going to figure out what's going on in the middle. And one of the clues as to what goes on in the middle of a polynomial function is the zeros. So the zeros of a function are the x-intercepts or the solutions of the equation. So if I ask you to use substitution to determine whether -1 is a zero of this function, what would I do? What does that mean? Well, it means that you're going to sub -1 in for x. You're seeing if this x value is a zero of the function. If it is, when I plug -1 in for x, I should end up with 0, right? That's why it's called the zeros. It's what x value gives you a y value of 0, or what input gives you an output of 0. So let's do it. We get 2 times -1 cubed minus 3 times -1 squared plus -1 plus 6. If I do this, I'm going to do it without a calculator. You can do it with a calculator, but I want to notice a couple things because you're going to be doing this a lot this chapter, is that when the exponent is odd, it'll stay negative. So this will be 2 times -1, which is -2. When the exponent is even, then it'll go positive. So this will be -3 times +1, and then plus -1 plus 6. So -2 minus 3 minus 1 plus 6 is 0. So yes, -1 is a 0. In other words, when you plug in -1, you get a y value of 0. Or when you plug in -1, you get a y value of 0. Same sentence. Okay, so now we know what makes something a 0, right? It makes your function equal to 0. Let's see if we can find them. So always, same in chapter 3, when you're finding zeros, the first method we always use is the principle of zero products, which is found when your equation is factored. So all of these functions are written as a product of linear factors. In other words, we've taken our equation, or our function, I should say, and we've factored it to its linear factors. Linear meaning that each factor is linear. Each exponent has the highest exponent of 1. Okay, so this is fully factored. We could write this out as x times x minus 3 times 2x plus 1 to make it purely linear, but putting as x squared just kind of groups them together. Okay, so now we want to find what the zeros are. To find the zeros, the first thing we should do is set it equal to 0. Right, so we're finding when is y equal to 0. So what x values give me a y value of 0? Well, using the principle of zero products, that means that if any of the factors are 0, then the whole thing is 0 because they're all multiplying. So then we take each one. We say, what makes x squared equal to 0? Well, plus or minus the square root of 0 is still just 0. What makes x minus 3 equal to 0? When x equals 3. And what makes 2x plus 1 equal to 0? Well, subtract 1 to get 2x equals -1, and then divide by 2 to get x equals -1/2. So the zeros of this function are 0, 3, and -1/2. All right, pause the video, give this one a go. Okay, so hopefully you did. And so what would make this equal to 0? When x is 0, x equals -1, x equals 4, and lastly, x equals 1/3. I like to write them in numerical order, so I'll often say x equals -1, 0, 1/3, and 4. And if you're looking at the back of the book, they should be written in numerical order as well. All right, so what do you think the next logical step is? It's for us to factor. So if you hate factoring, don't worry, you don't have to factor. But trust me, once you see the process of solving otherwise, you're probably going to want to factor. So the first thing you do to factor is let it equal to 0, or to solve using the zero product principle is make it equal to 0. So 0 equals x cubed minus 2x squared minus 9x plus 18. Oops. Plus 18. Okay. Now, to factor, you always try to greatest common factor first. Greatest common factor first. These 4 terms don't have a greatest common factor, so then I move on. Are there 2 terms, 3 terms, or 4 terms? Because there's 4 terms, we know that we have to factor by what's called grouping. Grouping goes that you have to break these 4 terms up into 2 groups of 2, and then greatest common factor them individually. So out of this first group, I'm going to pull out an x squared. If I pull it out, it goes out front. I'm left with x minus 2. Out of this group, I'm going to pull out a 9. Now, because this first term is negative, I'm going to pull out a -9. So I'm going to pull out a -9. I'm left with x minus 2. if you've done it correctly, you will be left with two terms that have a greatest common factor. In other words, the bracket has to be the same. If the bracket's not the same, you have not done it correctly, or it wasn't factorable by grouping. So I'm going to pull out that x minus 2, and I'm left with x squared minus 9. Now, it has to be a product of linear factors. So this one is not linear, so I can go further. So from a factoring perspective, to go further, I can notice that there's two terms and that this is a difference of squares. If you don't know what I'm talking about over here, please talk to me. I can help you with this, but I don't know, kind of where you're at with your factoring, right? So it's either a difference of squares. It could also have been a sum or difference of cubes. And then if there's three terms, you're going to use the AC method, if that sounds familiar. Okay, all right, but this is a difference of squares. So to factor a difference of squares, I'm going to go x minus 3 and x plus 3. So you draw two brackets, square root of the first term, square root of the last term, one gets a plus, one gets a minus. Now it's a product of linear factors, and I can solve. This would give me x equals 2, this would give me x equals 3, and this would give me x equals negative 3. I could write them in numerical order, would be ideal, but I also want to show you that if you really hate factoring, you could have, like when you had this thing here, 0 equals x minus 2 times x squared minus 9, you don't necessarily have to write them as linear factors. Linear factors is when you know you're done factoring, but you could have pulled out here and said, hey, this would be x equals 2, but you could have also taken this one and said, what would make x squared minus 9 equals 0? Said when x squared equals 9, and when x equals plus or minus the square root of 9, or plus or minus 3. So I could have gotten the plus or minus 3 from here. You don't have to factor. Okay, I was just being a purist and solving by factoring, but really it just said solve, right? So I can do whatever I want to get my 3 answers that I got for that. Okay, so what about this one? Well, this one, there's no greatest common factor again, and now I see 3 terms. Now I see 3 terms, and I think, is this a trinomial? So you have 2 options at this point. At this point, if you're like, oh, it kind of looks like one, but isn't really, you can be like, oh yeah, it's that u substitution thing. So you could make it equal to 0 and say that u squared plus 4u minus 45 equals 0. Minus 45, right? And I let u equal x squared, right? So that middle variable. And then I could solve this. So I'm going to solve by factoring again. So this one I don't have to do a whole AC method because I can just draw my 2 brackets because I know it's u times u. And then the 2 numbers that multiply to give me negative 45 and add to give me positive 4 are positive 9 and negative 5. Now, this is what u equals. And so I would keep going. I'd say u equals negative 9 and u equals 5. But I wasn't solving for u, I was solving for x squared. So I would replace the u with an x squared, and I'd say x squared equals negative 9 and x squared equals 5, and then I would solve. X equals plus or minus the square root of negative 9, which of course simplifies to plus or minus 3i, and then x equals plus or minus the square root of 5, and that's as far as it'll go. So this one had 4 x-intercepts. Now, if you didn't need the u substitution, some people are okay with it being x to the 4. They're like, okay, x to the 4 plus 4x squared minus 45. And they're like, I can recognize that it's quadratic in form, so I'm going to actually just factor it straight away. And they can say, okay, the 2 things that's multiplied to give me x to the 4 are x squared times x squared. And then they just say the 2 numbers that give me 45 would be negative 9 and positive 9 and negative 5. Positive 9 and negative 5. And then we're at the exact same place that we would be, right? You'd say x squared equals negative 9, x squared equals 5, and you'd still get x equals plus or minus 3i, whoa, and x equals plus or minus root 5. So if you don't need to do the u substitution, you don't have to. But chapter 2 got you ready that you can recognize something as quadratic in form, and then you are allowed to use a u substitution so that it's easier to factor. All right, moving on. Okay, even and odd multiplicity. This is again something that I find easier to show you on Desmos before we write the stuff in here. So again, what we're trying to do is come up with graphs of polynomial functions. We know their end behavior. We now know how to find what the x-intercepts are in the middle, but we have to fill in the gap of like, well, what does that mean? Is going to happen at those x-intercepts. So let's look at an example. Let's look at y equals, let's just go x times x minus 3 times x plus 5. Okay, so here's my graph. Okay, this is an odd positive graph, so it starts in quadrant 3, ends in quadrant 1, and it's got 3 x-intercepts. It has an x-intercept at 0, 3, and negative 5. 0, 3, and negative 5. Cool. What's it doing at all these x-intercepts? It's just passing through them all. Well, what happens if I change these x-intercepts to squared? So if I just change that 1, now the 0 at 0 did something funky. Instead of my graph passing through, it did this weird turning around thing. We call this being tangent to the x-axis because it never crosses it, it just runs along it. Okay, so it never crosses the x-axis, which makes it a tangent. Versus this x-intercept at negative 5 still goes through. This x-intercept at 3 still goes through. Now this is now an even positive graph, so started in quadrant, sorry if I show you the whole picture, let me zoom out. It's now even positive, go 1, 2, 3, 4 x's, so it starts in quadrant 2 and ends in quadrant 1, right? But it also changed what happened at the x-intercepts. So what if I made this x minus 3 squared? Oh, now 2 of them are tangent. What if I make this one squared as well? Oh my goodness, now they're all tangent. Okay, so something about this exponent on your factor changes the behavior at that x-intercept. Okay, so it's really easy to change the behavior by just taking off the exponent. So it's this exponent, which we call the multiplicity of the 0, that determines the nature of that graph at that 0. When the exponent is 1, the graph crosses the x-axis. When the exponent is 2, the graph is tangent to the x-axis. Okay? In other words, it doesn't cross through. Let's see what happens. What if I put a 3 in? So let's get rid of some of these 2's. Actually, let's keep 1. So let's keep the negative 5 as a multiplicity of 1. So the exponent on the product or on the factor is a 1. Let's keep the 0 as a 2. Let's change the 1 at 3 to a multiplicity of 3. So it's similar to the x-intercept at negative 5 in that it crosses the x-axis, but it kind of does something a little bit funky, and I'll zoom in to show you. So this is my x-intercept at negative 5. It's just straight through. This is my x-intercept at 3, and it does this weird flattening out thing, but it still crosses the x-axis. What if I was to do an exponent of 4? Let's do another 0. Let's do one at 1, so go x minus 1. And let's do this one is going to be an exponent of 4. That one's similar to the exponent of 2. In that it didn't cross through the x-axis. So here's our rule. If you're an odd multiplicity, in other words, your linear factor is raised to an odd degree, you're going to cross the x-axis. If your exponent on your linear factor is even, you're not going to go through the x-axis. You're going to be tangent to the x-axis. And then even more so, let's keep this basic, y equals x. Right? Your straight line passes through the x-axis. Y equals x squared. What did it do? Tangent, right? It doesn't go through the x-axis. It turns around on the x-axis. If I change that to a 3, there's my flattening out. I'm going through the x-axis, but it does a little flatten out. Now you can actually go higher. I can do a 4, tangent. I can do a 5, flatten. I can do a 6, tangent. I can do a 7, flatten. And now it's flattening more, but it's just flattening, okay? We're just sketching. 8, tangent. 9, flatten. So now we can come up with a general rule. We can say that when or if x minus c to the k is a factor of the polynomial, now the k value, the exponent has to be greater than or equal to 1. We have to have whole number. Now we don't start at 0 because that just wouldn't exist. So 1 and up. Then we can use these rules. If this k is odd, then your graph is going to cross the x-axis. If the k is even, it's going to be tangent. And now I'm going to go one step further. If the exponent is a 1, we say that this has a multiplicity of 1 and it's going to cross the x-axis. If the exponent is a 2, we say there's a multiplicity of 2 and it will touch the x-axis, so it'll be tangent to. I call it just touching because it feels easier. And then if the exponent is 3, it's a multiplicity of 3 and the graph will flatten. You don't have to have this memorized, right? Y equals x, multiplicity of 1, passes through. Y equals x squared, multiplicity of 2, graph touches. Y equals x cubed, multiplicity of 3, the graph flattens. This is on your formula sheet, right? They're your base graphs, y equals x squared, and y equals x cubed. So now we're going to use this to determine or to find the zeros, state the multiplicity, and determine their nature. Really, from a textbook point of view, you just have to find the zeros and state their multiplicity. I'm going further and making you determine their nature because it's what we're going to be doing in the next section, so in 4.2. So if I look at this polynomial function has two zeros, when x equals 1 and when x equals -2. X equals 1 has a multiplicity of 3, okay, which means the graph will flatten but cross through the x-axis. This x-intercept of -2 has a multiplicity of 1, right? So a multiplicity of 1, which means it will cross through the x-axis or pass through the x-axis. I don't care what language you use. So if we went further, we could now sketch our polynomial functions. This is a 1, 2, 3, 4th degree equation. This is a 4th degree, making it even. The coefficient is positive, so it's going to start in quadrant 2 and end in quadrant 1. Now I have an x-intercept at -2 that's going to pass through the x-axis. So starting in quadrant 2, pass through the x-axis, come back towards the x-axis, and look, at x equals 1, we flatten out a bit, and then we end in quadrant 1. So the end behavior, you have to know where to start, but if you do your multiplicities correctly, your graph will end in the quadrant that it should. If it doesn't, like if this had ended up in quadrant 3 or 4, then you're wrong, right? Then it would be an odd negative graph, and it's supposed to be even positive. So let's try this guy. So the first thing we're going to do is pull off our x-intercepts. This is an x-intercept of 0. This is an x-intercept at 3 halves, right? 2x minus 3 equals 0 when 2x equals 3 when x equals 3 halves. And this one is an x-intercept of -2. So that's already what we learned. Now the layer we're going to add is the multiplicity. The multiplicity, I often shorten to just m. So this one has a multiplicity of 2, right? This one has a multiplicity of 1, and this 0 has a multiplicity of 3. From the textbook perspective, 4.1, that's all you need to know. I want to tie it all together. So again, this is how we're going to start 4.2, but it's never bad to hear it a million times. So again, done 4.1. 4.2, we're going to use these to graph. So I'm going to write my x-intercepts in order. So I'm going to put x equals -2, x equals 0, and x equals 3 halves. I find it a lot easier when I go to sketch if they're in order. So the x equals -2 had a multiplicity of 3. The x equals 0 had a multiplicity of 2. And the x equals 3 halves had a multiplicity of 1. What does that mean about the nature of my graph? Well, when the multiplicity is 3, I think of my x cubed graph, and it flattens, but also crosses through the x-axis. When x equals 0 and I have a multiplicity of 2, that's going to mean it's going to just touch the x-axis. Think of your y equals x squared graph. When the multiplicity of 1, I think of a line, and it just crosses through the x-axis. So how would I then use that to sketch? Well, this is a 1, 2, 3, plus 3 is 6. So this is a 6th degree, which makes it even. The leading coefficient is negative, so it's an even negative graph. So it's going to start in quadrant 3 and end in quadrant 4. Okay, so let's put on my x-intercepts. I have an x-intercept at -2. I have an x-intercept at 0, and I have an x-intercept over here at 3 halves. I don't actually care where. Okay, it's just a sketch. So I'm going to start in quadrant 3. It's going to end in quadrant 4 with me, and I'm going to use this behavior. I'm going to flatten but cross through. I'm going to touch, and then I'm going to cross. So I'm going to flatten and cross. I'm going to touch, and I'm going to cross. And that's my sketch. It looks horrible, right? But it's a sketch. It started in quadrant 3, and as long as I started in quadrant 3 and had the right multiplicities, the right behavior, look, I ended in quadrant 4. Sweet. I went through my x-intercepts, and it looks super funky, but it's all right. You could use Desmos to check to see if you did it correctly. So if I open my Desmos, right, just move that over. So the equation is y equals negative 2x squared times 2x minus 3 times x plus 2 all cubed. All right, close? I don't know. Let's see. Well, starting quadrant 3, ending quadrant 4. It flattens out at the x-intercept of negative 2. It touches at 0, and it passes through at 3/2. So yeah, it did something funky here. Like the second, the absolute max here went all the way up to like 58, which mine looks pretty equal to the other one, but it doesn't matter. Because by the end of this chapter, where we're going with this is that all I'm going to care is that in this region, the graph was above the x-axis, and in this region, the graph was below. I don't care how high above, I don't care how low below, but I know I have it in the right spot. So even though it doesn't look like the graph, it's a sketch, and it's good enough. All right, so now you're ready to do part 2, and that's it for 4.1.